Good evening all, and welcome to tonight's BTS evening lecture on historical tunnel construction, building tunnels in the 19th century. Tonight's speaker is Peter Harris, who is a director of COWI UK. Peter Harris studied civil and structural engineering at Bradford University. After a short time at Nottingham University, he worked for the National Coal Board, British Coal, for 13 years, doing both surface and underground works, and for his last 3 years there was attached to the architects department. He then worked for 6 years for a small structural consultancy, designing numerous portal frame buildings and teaching part-time at Burton-on-Trent Technical College. He has spent the last 24 years working for Donaldson Associates, and after they were taken over, for COWI, a Danish consultancy. During that time, he has carried out design work for new shafts and tunnels, has specialised in work for Network Rail in maintaining and refurbishing their Victorian legacy of tunnels. Thank you, Peter.
Right, well, hello, my name is Peter Harris. Thank you very much for the introduction, Kate. So what I'm going to talk about tonight is historical tunnel construction, how tunnels were built in that period from 1780 up to about 1890. I will talk about shafts, head-ins, the construction of the main tunnel, and if I have time, I'll talk about some separate construction features. The sources of this talk is for the Sims Practical Tunnelling, written in 1845, and I've used the third edition, 1896, and that's where most of the illustrations come from. Also referred to Gripper, railway tunnel in heavy ground, which I may explain later. And a couple of things from Walker, who was the resident engineer on the Severn Tunnel and talked about its construction and the problems they had. And that was written in 1888. And one of the other sources I've used is the website Forgotten Relics, which is run by a friend of mine called Graham Bickerdike, and I'll show you some of his photographs later. So if we start with this illustration, this is one of the front cover of the Sims book, the works at Bletchingley Tunnel in 1842. And this is a nice little picture because it shows several interesting features. Firstly, you've got this tower here, which is a sighting tower. And then you've got a winder, a horse gin, with horses going round in a circle, pulling ropes on a drum. And that's where the shaft is, just there. And in the foreground, you've got a wagon with some very heavy logs on it, some very large timbers, and you'll see those in use later on. I think the problem at the time was building a tunnel from two portals. If you build just from portals, you've only got two working faces, and at those working faces you can only have either a team of miners or you could have a team of bricklayers, and that's going to take a long time to drive the tunnel. So very quickly they came up with a system of sinking extra shafts. At the high point of whatever hillside you're going through, you're going to construct a sighting tower. And that will allow you to set out all these shafts. Now this is Bletchingley with 12 shafts. The more shafts you have, the more faces you can have, and you can move your workforce, your miners and your bricklayers from one face to another. That's a close-up of the sighting tower. Basically, it's a stone masonry core, tapered up to a platform, and around that, a timber tower to keep basically the wind off the equipment. And in the top of the tower, you've got a window for sighting through, and you've got a transit theodolite. Picture on the left, that's a transit theodolite, very hefty frame, bolted down. You've got leveling screws, and your telescope can rotate to 180 degrees. And you can see it here again in this second illustration, a slightly different one. It's got leveling bubbles across the top, and the thing can rotate to 180 degrees. This is a sighting tower at Bramhope Tunnel, built in 1845 to 1849. This is a stone masonry one. It's one of the very few that still exist. At the top, you can see the large slot through which you'd be sighting the theodolite. This is a little timber-clad one on the plans for Holland Tunnel in 1856. So basically, having set out the line of where the railway is going to be, you build your sighting tower on the highest point, and you can sight down forwards and backwards to establish the actual line, and you get your theodolite spot on the line, and then from there you can sight down to other points on the ground accurately to know that would be where you would set out the shafts. Having decided where your shaft's going to be, you build a timber frame on the ground. This is a cross frame here. Shafts were, for railway tunnels, very commonly 9 or 10 foot in diameter. There are some much larger ones on some tunnels, such as Kilsby, but 9 and 10 foot diameter is the most common. And having set your frame on the ground, you'll excavate down as far as you possibly can in the ground, and you put a timber curb in. You'll then hang that timber curb from your top frame with cast iron rods. Actually, one tunnel they used willow rods, but you'll hang that frame and then you build the brickwork back up to ground level. Having done that, you then excavate down. You've got your timber curb placed on the hangers, excavate down in the middle, excavate out, prop it. You go down as far as you possibly can and put another timber curb in, and then progressively you either brick the whole thing up or you brick it up in panels as you excavate the material out. That's a rotten timber curb that's still left in place at Manton Tunnel, built in 1848. And as you can see, the timber there is now progressively rotting, and that's eventually going to cause some problems and have to come out. So you excavate down from your winders. I've shown a little horse gin winder here over each shaft. This is a steam winder at Catesby Tunnel. This is a little bit later. It's 1897 in Leicestershire, and we're lucky to have some photographs there. That's the actual shaft going down to the tunnel. They've got a temporary track there for moving the waste, but the actual winder is in this little house here, a steam winding engine. And this is also at Catesby Tunnel. This is actually a little steam crane over the top of the shaft. And there's the workers going down in a kibble. Very good health and safety situation there, hanging on and waving to the cameraman. But this is a typical sort of thing that we'd use early in the period, a horse gin. You've got a frame with a winder drum on the top and two horses going around in circles to wind the ropes back onto the drum. And you've got a frame, and that's the actual shaft. And there's a man controlling the rope going down, and a labourer taking away some of the spoil that's just been wound up. So you progressively work your way down, building a brickwork, put another frame in, put some more brickwork in until you get to the level of your tunnel. This is an illustration from Llangeffelloch Tunnel, much later, 1913. But here they were working in rock, so rather than keep hanging the shaft on the cast iron bars, they actually built elephants' feet every so often into the rock and then transferred the load into the rock. So having got that, you've got the brickwork almost down to the level of the tunnel, probably also working in from the portals. I've only shown two shafts on this illustration, but you can obviously have an awful lot more. I think the most I've ever come across is 34 at Bletchingley Canal Tunnel. So progressing down until you're almost, this is where the tunnel arch will actually be. So you're going to stop a few feet above that, metre or two, and you're going to insert a timber frame. And this is again going to be a cross frame going both ways. These are 13-inch, 375mm size timbers, and they've got scarf joints here and there. So you excavate out this very small pocket and insert the first piece of timber and the other one, and then put the one with the scarf joint. and another one going the other way. So you're actually carrying the last bit of weight of the shaft into the ground above where the tunnel's going to be. And you've done all that work, all that in brickwork above. And that's a plan of one of those frames with just a simple cross frame supporting a 9-foot diameter shaft. After that, and you've got that frame in place, that's where the tunnel out is going to be. You'll then carry on the rest of the shaft down in timber square work, cross frames and boarding all the way down to the bottom. And perhaps you might build a sump at the bottom. And this one shows a nice little winder here with actual winding handles. So 2 men would be operating that. And they're winding up buckets of waste as they've excavated the shaft down. So after you've got to the bottom and built a sump, you then go to excavate from one shaft to another and form a timber heading. And you'll connect all the shafts and possibly the portals up all as well with a timber heading. You've got to set that line of that out accurately. So having had your theodolite on the ground to set out the position of the shaft, you'll be able to accurately mark on 2 pegs where the actual centre line of the shaft is, and you'll drop wires down the shaft to the bottom and put a large plumb bob weight on that. You'll suspend that possibly in a bucket of oil or a bucket of soft sludge to stop it vibrating. And when those the wires have settled to stop moving, you'll then be able to mark out the centre line of your shaft at the bottom and construct the heading in between them. And this is a typical heading. Headings were usually quite small in the start of the period, as small as possible, and they do get larger and larger during the 19th century. This one's probably about 5 foot by 3 foot, framed out in rough timber and boarded out as well. And occasionally you put a cross piece on, suspend a candle down from one of the frames, and sight back to the 2 wires that you've dropped down the shaft. And that will give you periodic checks on where the centre line of the adit should be. And here's typical illustration of the time: 1 man excavating, another man shoveling the waste into a tub, and that's running on little timber rails through the heading. But again, you see how small this heading is, probably 5 foot by 3. Very poor working conditions for the guys who are actually building this. Eventually, you'll have the situation where you've connected all the shafts all the way through, right out to the portals. I'm sorry about the quality of this one. At this stage, having brought the brickwork down and got the headed through, you're going to start excavating out from each shaft. So in this case, you'll then have 6 faces to excavate from. Just talk a little bit about profile. This is a soft ground tunnel. This is Bletchingley on the left and Saltwood on the right. 2 slightly different profiles. These are soft ground tunnels because they've got an invert to brace the sidewalls. And occasionally somebody will say, oh, it's an elliptical shaft or it's a parabolic shaft. Sorry, parabolic tunnel. They're never parabolic. They're always made up of circular curves, so they're not even sometimes elliptical. And basically, in the crown here, you've got a 9-foot radius, and that's the centre of that radius. And then you'll transfer that to the haunch with a 15-foot radius, and you project the lines down, and you have 2 centres. And eventually, you'll go down to the sidewall. If it's in good ground, hard ground, you probably make the sidewall vertical. But in this case, we've got a curved sidewall with a radius of 21 feet, and that's the centre of that. Sometimes the radius of the sidewalls get quite a lot larger. 30 feet isn't uncommon. So they're built up of circular curves, and the invert is also on a circular curve, and that's its centre there. So that's how the engineer would look at what shape tunnel I want to produce. And they use circular curves because in the Victorian period they're easy to set out. But the miner, he needs something different. He can't be working to these dimensions. What he needs is offsets from the top. So here, marked in 1 foot increments down from the top of the excavation is a horizontal distance. So the miner knows that at 1 foot down, he's got to go 4 foot 8.5 inches wide. At 12 foot down, he's got to go 13 foot 10.5 to that point. And that's how the miner would actually work, to those dimensions. Just in passing, a brick invert to brace the sidewalls, and a circular drain built in a brick arch. And this is a fairly common southern England feature, and I might mention North England features later. Having done that, having set out how he's going to build it, the miner is going to excavate a little passage, a top heading, and he'll insert timbers to cover himself. That'll be braced back to the timber shaft and bored out and prop. And then progressively, he'll make the excavation wider, insert another timber and prop. Keep working out. And that's a typical miner with a clay spade there, excavating out, ready for his other bracing, and one of the timbers are above him. This is a later illustration. This is further along, but in working from the timber shaft, you would excavate out that top pocket, that top bench, and you put some timbers overhead and then bored out between them, as shown in that previous illustration. Now these timbers can vary in size: 12-inch, 15-inch, 18-inch timbers, and they're just round tree trunks. And this is referred to as a length. And lengths vary from 8 feet, 10 feet, 12 feet, 15 feet. I think the longest length I've ever come across is about 17 feet. 12 and 15 feet are fairly common, and it depends on the quality of the ground. The stronger the ground, if it's really good firm clay, the longer you'll be able to work. And this is where the phrase heavy ground that's used by gripper comes in. It was a term they used at the time for what we would now think of as ground that's not very good. It's not any heavier than any other material. It's just weaker and puts more load on your timbers. So in heavy ground, that advance could be quite short. 8 foot is not unreasonable, but in good ground, you'll go as far as possible and use as big timbers as you possibly can. Having done that top bench, you then work down, excavate out, and form another bench. And as you do this, you'll be demolishing your original timber heading. I should have mentioned earlier that this is referred to as the English method. In the English method, the actual heading connecting all the shafts is at the bottom. If you're in France or Germany, they put their heading through at the top, and there are some slight advantages in doing that, but overall it causes a lot more problems with drainage. But here they are in this illustration, taking out the second bench, getting the props ready to move forward. And then you are progressively going to work away from the shafts and build all these sections. But in soft ground, as well as being limited by how far forward you can go by the strength of the ground, you've also got to support the face temporarily. So this is an elevation showing the timbers that you're using to hold the ground up, and the face, the top bench, you've got 2 raking props there, a lower bench, 2 more raking props. And that's a heading that you've driven through. And also on this illustration, you can see 2 molds. These have been marked. This one's L, and this is a ground mold, and it gives you the dimensions to build the invert, and the bricklayers will work to that. And you also got a side piece in here, temporarily supported, and that's going to give you the profile to work to do the side walls. So they're just a couple of profiles at each end of your section to work for the bricklayers to work to. So the miners will finish. Their gang will have got all this timber complete. They'll go to another face and work there, and the bricklayers will come in. This is a detail called a skewback. This is in brick. It's to form a connection between the invert and the sidewall. And the bricks for all this section, the 2 parts of it, are actually put together on the ground in a mould, and then they're saw cut to that profile and saw cut to that profile. They come down as a kit, and the bricklayers will build that one, build the invert, build that one, and then build the sidewalls. And this illustration shows the bricks as complete. Perhaps in this one, they've been able to draw the timbers out at the side, or perhaps the ground was good enough for them not to need them. They've still got the face boarded up. And at the top here, these timbers are still in place. And they've built little pillars of brickwork in between them to support the timbers, the laggings you've got the other way. This illustration shows the another tunnel where it's still got all the timbers in for the sidewalls as well, and they've put the centering pieces in. Now this helps them build the top part of the arch, and there'll probably be 3 or 4 of these frames in a length, supported on vertical columns built off the invert. And when you're building the sidewalls, you can build those in free air because they're not quite vertical, but they're sufficiently vertical for you to, the bricklayers, to lay the bricks without any support. But once you get to this level of Springer, you're going to have timbers to support it. So having put the centering in, you'll lay the first lagging here and build that brickwork. Lay another lagging, build another one, and progressively keep putting more laggings in between the centering frames and build the brickwork up towards the crown. At this stage, you've still got the shaft supported on these timbers. And these are typical centering frames from the 19th century kits of timber with cast iron or wrought iron plates, and they can take them apart and move them along the tunnel as necessary. And that's more of a king post truss type frame. This is a photograph from one of my colleagues at Network Rail, and it's described as being the timber structure used in the construction of the lining of Doveholes Tunnel. I don't think this is the timber frame for the original lining. I think this is a timber frame for a repair works to the lining. But you've got some fairly hefty timber frames, and you've got laggings in between them, and they've got a tub track down the middle. Just as a little aside, this is Standedge Tunnel. This is a south tunnel, which is single track, and it's got a little brick drain down one side. Sidewalls are vertical because it's in fairly good ground, and that brickwork is all bonded through English bond. Once you get to the arch, the number of bricks in that ring, the number of bricks in the next ring are all different. So there are more bricks in each ring. But very occasionally you will get places where you might have, say, 12 bricks to there and 13 bricks in the other ring, so you can put a bonding brick in, and this happens intermittently. This is double ring bonding at Clifton Hall Tunnel built in 1850. Unfortunately, this tunnel, part of it collapsed in 1953, and 5 people in the houses above collapsed and died into the failure. This is double ringing, double 9-inch rings with vertical bonding that's referred to in panels going through to connect all the rings together. Here above, you've got the actual boarding for the excavation where those big timbers would be, and little brick piers in between. And there's a nice little note that says rubble packing. And I'll explain why, but as far as I can see, that's almost impossible to get that packing in there. And another feature here, rather than that half-arch drain in the south of England, this is north. North of England is usually vertical brick walls with stone slabs for the central drain. Of course, there's a problem that as you're building the upper part of the arch, you've got one gang working on the left-hand side arch, one gang working on the right, and eventually you come to nearly the crown and you've got to join it all together. So your lagging at that point will have a rebate, and you have little timbers that go the other way, and you've got to fill that piece of brickwork, and that's a fairly tedious piece of work to do, because you've got to lay the bricks overhead. And physically, as you put those little timber boards in, only really one man can work on this at any one time. So the guy who builds a crown, he gets paid more than anybody else because he's doing the most difficult piece of work. And this would be the situation that you've got then. you're working away from the shaft. You've got the square work for the shaft. You've excavated both ways. You've got your timbers in, and you've boarded the face up, and you fill the brickwork arching with those centering arches there. And then you do the same on the opposite side until you've got both sides done. And you leave the piece in the middle. That's called the shaft length. And you do that last. You get the two pieces done each side, and then you can frame that out and build the brickwork in there. And at that time, you also fill in the brickwork right up to the bottom of the shaft as well. Having done that, it's a question of repeat each side, each time. Again, you'll do a little bit of a top heading as far as you feel you can go, and then those timbers that were over the previous brickwork, you'll use these bars and you'll drag them forward as you excavate out the top bench. And you'll keep pulling those forward. Again, drag them forward, excavate out timber, brace that back to the invert, excavate that bench out, brace that back, excavate the bottom, demolish the timber heading as you go. That's the next section. You've got the brickwork built for the invert, built the side walls, put the centering up, build the arch, fill the crown, and it's just a question of repeating that process every 3, 4, 5 days. Again, the miners will do all the excavation and timbering. They'll move somewhere else in the tunnel, and the bricklayers come and lay all the brickwork. Completely separate trades, and they're run as little subcontracts by a man called a butty man. And in effect, it's lump labour, as we used to have in the construction industry in the 1960s and 70s. Each one's a separate little subcontractor. These timber braces are only temporary, and they're notched into the invert. And at Highville Road Tunnel, when we stripped all the track out and stripped all the material below track level, we actually found all these pockets because the bricklayers hadn't filled them in. As they moved on with the tunnel, they left the holes in the invert. And we could see which way they sloped, and we used that to actually locate a hidden shaft. So working away from shafts, more shafts you have, more faces you can have. At some time in the mid-1850s, 1860s, they moved away from that. And having sunk the shaft down and got the adit through, instead they did a thing called a breakup. So you could have even more faces. You'd actually break up between the shafts. In this case, that would give you 10 faces to work from. This is an illustration by Thomas Walker on the Severn Tunnel. And here he's showing how they did the breakups there. So having built the bottom heading and got that all the way through, that's it in elevation, you would then take out part of the roof of the heading and excavate upwards in a series of benches and across. And having done that one way, you then go back the other way. And then the big timbers that you use to hold the ground up, you would bring them along the heading, up the riser there, and start bracing out at the top and get the top timber in. And then, as before, work left and right, progressively making the excavation wider and putting more timbers in, until eventually you've got a whole section timbered out, and then you can work from there, build the brickwork and work away. And eventually you could end up with this nice situation where you've actually got the tunnel built, all the brickwork all the way through, all the shafts connected. I've been talking about soft ground tunneling mainly so far. This is McKean's rock drilling machine at the San Gotthard Tunnel in 1875. This is a compressed air machine. You'll have a steam engine in the somewhere in the tunnel, and that'll be working a compressor, and then that'll be able to run rock drills. And this one's got four rock drills on it, 2 on each side. And this is similar to the that used by Captain Beaumont at Queensbury Tunnel in 1870. And Queensbury Tunnel near Bradford was the first real tunnel that was driven through harder ground with a proper rock drill. In harder ground, when you're using drills like that, or previously hand drills, you'll be using black powder to blow out the rock. Later on, 1870s, you'll start to get early versions of dynamite like Tonnite. That was used on the Severn Tunnel. And you'll get overbreak. It's not as accurate as digging through sands and gravels and clays. So this is actually down here. That's the actual roof of the tunnel from the outside. And this is a little brick pier, 550 mil high, stood on the back of the lining, another one there, holding up the rock. So sometimes the overbreak can be quite large. This is the overbreak at Beauchamp's Tunnel. About 12 to 15 feet of overbreak through a very, very difficult geology. It was through a syncline. And the amount of overbreak they had there was astronomical. And the trouble is, after the tunnel was finished, that's the original brick lining, that some of this rock continued to drop, and it actually started to distort the tunnel lining. And then in 1950, they broke into this void, which they didn't know was there, and they actually put a concrete saddle over the back of the arch there. So in hard ground, overbreak can be quite large. This is a classic single track tunnel portal. Very nice architectural design with the fuzz wires around the face, through the cut-in, and very shallow swept back wing walls stepped into the ground. That's a fairly popular design, but doesn't do much to brace the actual portal. And the problem with that design, if we look at a cross section here, that's the actual dimensions of the actual wall, and that's the line of your tunnel. You've got a slope above it, and you've got a little drain, and they're your architectural features for the portal. And with those flat-faced portals, you often get a problem where the ground pushes on the back of the wall, and the tunnel lining cracks periodically in that section there. And that's a typical Victorian tunnel portal being built. Just a very small timber frame, lots of timber lagging, just temporary work so they can actually get the main tunnel done. Then afterwards they'll come back and build the architectural portal afterwards. This is a much better design. Again, very robust design for the fuzz wires. Much more curved side walls, giving a lot more bracing, much more stable structure. This one, it shows an inner curve because that's actually the tunnel profile there. And then you've got this extra raised up area here. You've got a bell mouth at the portal. And that's shown on this drawing. So that's the actual normal tunnel profile there. And just for the last, 36 feet, 9 inches, the tunnel profile gets higher and higher. And that bell mouth was quite a common feature. Brunel did it on quite a few tunnels because they were concerned about the air pressure effect of driving a train at 55 miles per hour into a tunnel. And they were concerned that would try to create a pressure wave which would upset the drivers and the passengers and might cause a problem to people hearing. With trains running at 50, 55 miles per hour. And now we're talking about 125, 180 miles and 200 mile per hour trains. And we're looking at building bell mouths again because we really do have dynamic shock waves now, which the Victorians imagined but didn't really develop. This is a classic pepper pot design on top of a shaft, built after the shaft had been completed, and nicely tapered brickwork with a corbel around the top and a cast iron and wrought iron grill over the top of it, to stop people throwing bricks down the shaft. And we've replaced quite a few of those now over the years because people are still trying to throw bricks down the shaft. And this is slightly unusual. This is at Manton Tunnel in Leicestershire. And having built all the shafts for construction, they decided that they didn't need any of them for ventilation, or didn't need some of them for ventilation. So they put a brick dome over it and, in effect, abandoned the shaft. And sometimes they brick them over at the bottom as well, and you can't tell where the shafts are. And this is an investigation that was done a few years ago. They saw cut with chainsaws a hole in the brick dome and did roped access down to inspect the shaft on the inside. But it's relatively unusual for the dome to be at ground level. This is a more common situation. So the tunnel's been driven. That was a construction shaft. Having finished construction, they've bricked it over. You can't see it from the inside. And so far up, they've built a brick dome at this level when they transition from the shale here into this light blue shale. And then they filled that with rubbish and abandoned it. And that then becomes a hidden shaft because you can't see it at the bottom and you can't see it at the top. And that creates a liability issue. We actually drilled into these shafts from the bottom at Up Holland, and we didn't find any brick domes. We found 2 tree trunks and a load of timber boarding, which, if that then rotted away as it was doing, all that material would drop down the shaft and hit the back of the tunnel lining. So at Up Holland, we've actually filled these with foam. And you don't get many drawings like this. This is Buckhorn Western Tunnel on the Salisbury and Yeovil Railway, a construction drawing recording what they actually went through. You sometimes get drawings showing where they've excavated to. You can find where they've reached with each day with the working away from the shafts, but they don't often record what they went through. And this is a very nice drawing. They've got 1, 2, 3, 4, 5 shafts. They're not at regular intervals, and they've recorded what they actually went through. And they've got bands of sand, rock and sand, loose rock and waste, bands of clay. And here they've actually built a top heading. Got no records of why they did it, but they actually built an extra heading in that section there, possibly for drainage. We'll never know. And also here at the bottom of the shaft, they've actually formed an invert in those sections there. And the rest of the tunnel doesn't have an invert. And again, we've been lucky with Buckhorn Western. We've got a cross-section view, and this shows the timber framing they used to build it, where the timbers were used to support the ground. And we've obviously transitioned from one type of ground to another here, because on this part of the tunnel, they've actually got an invert and no timbers on the outside. The drain here is a 12-inch pipe. This is a bit later, West Hoathly Tunnel, built in 1880, and the style has changed and the structure has changed. They've done away with the skew back in these areas here, and they've built the whole thing as one egg-shaped lump of masonry. Again, built in double rings, cross-bonded with what's called vertical bonding between. And the ground must have been quite good because they've only timbered out the top of the tunnel. And here, they've actually shown some squared timbers. I'd be very surprised if they actually used squared timbers. I would imagine they'd still use tree trunks. But yeah, so the ground must have been quite good because they've only got timber supports up in this region here. And again, they've shown the little plinth in the brickwork here to support the timbers that hold up the centering. And here the centering is a different type of kit. It's one piece frame all the way around. Occasionally in tunnels you'll see something like this. This is Conisborough Tunnel near Doncaster. You've got stone masonry sidewalls. If they could reuse anything they were excavating, they would reuse it. So the stone that they've excavated goes out, it's dressed in the cut-ins and brought back in to build the sidewalls. And the bricks themselves, I should have mentioned this earlier, if there's anything that comes out of the tunnel in the way of clay, they'll take that out, and in the cut-ins and elsewhere, they'll have furnaces, and they'll actually cast the bricks in the cuttings, and then bring them back into the tunnel. We found very often that the bricks in the early periods, the 1830s and 40s, are usually not very strong, 10, 15 Newton brick strengths. And as the period progresses, there's a definite trend that the bricks get stronger. And I think that's due to the quality of the furnaces that they used to actually cast the bricks in. But here, there's these timbers called biots, sometimes spelt boyots, sometimes spelt with an I instead of a Y. And these are timbers that have been, after the tunnel's been built for a few years, the line deteriorated, so they've excavated pockets and they've built in these the biots. And they're used to support a frame so they can actually reline it. And that is a construction joint. That's another one there. And that's that whole panel has been rebuilt at some later date. Some other features you occasionally get are these pieces of bullhead rail. They're in pairs and they run across the shafts. They're referred to as icebreakers. So there's two of these across the shaft, and 20 foot further up there'll be another pair perpendicular to these. Obviously the shafts act like drains and they catch any water from any strata that's water bearing, and it then runs down the inside, as you can see here, quite wet. And in the winter you'll be getting icicles forming. So eventually those icicles detach and drop down the shaft. So they put these bullhead rails across the shafts to actually try and break the ice before it hits the track. Something I haven't mentioned yet is what actually goes on where you connect a shaft to a tunnel. So you've got the vertical shaft and the tunnel running the other way. So you've got a feature which is referred to as the eye. And this is a frame built in cast iron curb or shaft eye in four components. So that's it in plan. It's built in a side piece, each side, and another piece that runs along the line of the tunnel. And that's them in elevation. So these are cast iron frames bolted together at these points. So having built up the brickwork fairly high up, you've actually got to stop work and insert this cast iron curb and then do the final bit of brickwork between that and the bottom of the shaft. This feature is very much a Robert Stevenson feature, and you see them all over the country. Severn Oaks down south, Claycross not far from Derby, Summit up in the Peak, Shildon is probably one of the earliest tunnels built by Stevenson, and Watford Fast. Cast iron is pretty good. It doesn't corrode that badly, but over the years these do start to weather, and we've had problems with some of these. But the sheer effort of getting these four pieces of cast iron up into the tunnel roof must have been really quite difficult. And that's a different sort of detail. You've got a nice this is a stone masonry tunnel, brick shaft, and then you've got this really nice stone masonry eye. This photograph is taken by my friend Graham Brickadike. This is from his website, which is well worth you looking at because there's such a wealth of material on tunnels all over the country on there. So that's a much more elaborate feature, reminiscent of the sort of thing you get in stone masonry bridges. And this is a brick eye, again courtesy of Graham. This shaft has been abandoned. It's been framed over at the top and buried at ground level, but a very nice brick eye. Interestingly, this brick up around the in a corner here is actually a bullhead curved brick, and in part that was done because during construction, even when you've finished this piece, you're still excavating elsewhere, all the waste has got to go back up the shaft. So you've got the ropes hanging down, and you wouldn't want to catch the ropes on the rough edge of a brick here. So the inner row of bricks is a nice rounded bullhead brick. Talk about a few other tunnel details. This is obviously a fairly good ground tunnel because you've got vertical sidewalls, you've got a little drain here, and you've got a centre drain, as I said, the northern feature, brick sidewalls and stone slabs over the top. This is from Brunel Tunnel, built in 1875. So the central drain would run down the 6 foot down the centre line of the tunnel, and whether it's a vertical sided or one of these southern England curved arches, when you get to the portal, you've got to transfer the drain into the cess and run along one side. So it'll run down the centre line, just beyond the portal, you'll get a cross drain. And that's a nice portal with a very, very strong raking brick wing wall. And again, you can see the dimensions of how thick that is, 3 foot at the top there, down to 6 foot at the bottom, inclined brickwork. This is Hampstead Heath Tunnel, a little bit later, 1903. As I said, with West Hoathly, they've done away with the skew back in this area here, and they've gone for this little vertical sidewall and brick arch drain here. And they've got this little feature here, a little nib of brickwork, and that was used to support the vertical props that supported the centering for the tunnel arch. They get left in place. This is my favourite tunnel, Bandage Tunnel up in north of England. Got the original Canal Tunnel, built in 1794 to 1811, with about 5 or 6 shafts. 1845 they came along and they built the railway, so they built single track tunnel, now referred to as a centre tunnel, and they built that without any shafts at all. And basically they built an adit, and all the waste material and went out through these adits into canal barges, and vice versa. The bricks came in on the canal barges and went in to build the tunnel. 20 years later, they decided that I hadn't got enough capacity, so they built the South Tunnel, again single track, built that from an adit from the centre tunnel, and again all the materials, waste went out through the canal and the materials came in. And then in 1890, that was still not enough, so they built my favourite tunnel, the North Tunnel, twin track, the slightly higher level, and they built an adit the opposite way. And there's no shafts on any of the other tunnels. All the material went through there. But of course, these tunnels don't always work terribly well. Things go wrong. Ground loading eventually causes problems. Sidewalls moving in. This is Gillingham Tunnel, not Gillingham. This is Gillingham in Dorset, and this is 1961. The invert, the bottom of the sidewalls had pushed in. There was no invert, so they actually built one, and they built it while the trains were running. They supported the rails on cross timbers, and excavated out and cast a concrete invert in short sections. This is Arley Tunnel in Warwickshire, another tunnel that failed. You can see the profile here, that's the actual tunnel, and it's completely flat in this area here. Arley Tunnel suffered from the effects of coal mine workings, so they put some temporary frames in to hold the arch. They built in situ concrete foundation set in pockets, and then they put pre-stressed concrete, precast concrete beams in between to support, to form a new invert. And we actually have the reinforced concrete drawings of those beams, and they've got hooks at the end so that they can be cast into a concrete pocket there. And all this was done while the trains were working in little bits. That's back to my favourite tunnel, Standedge North. Again, the tunnel was severely distorted in a very short section, about 20 metres long, and we replaced it with a precast concrete invert. in sections. We did one track at a time and then connected it all up. This is something hopefully you won't see very often. As times have changed, we've got higher sided vehicles, higher sided freight, in particular W12 gauge. And sometimes we're finding problems with the tunnels not being big enough, or particularly in this haunch area. The vehicles will catch on the side of the tunnel. And this is a detail at Copenhagen Tunnel, done with special permission, with cast iron plates put in, just in this area here near the portal. Southampton Tunnel's got quite a lot of that sort of frame, and it's generally the rail regulator doesn't like this as a detail, but he agreed to use it to allow Network Rail to use it at Copenhagen, because it was only such a very short distance that needed enlarging. That's the same sort of thing, detail done in precast concrete blocks, again to give more clearance to the train envelope, sometime in the 1960s. We've got absolutely no records of that at all. And this was Ore Tunnel in near Hastings, 1946. Again, they had a clash between the vehicles and the sidewall of the tunnel. So they broke out a piece of the sidewall. They inserted a bullhead rail to support the brickwork and put old rails going the other way as buyouts. Anyway, at long last, we've got rid of all that, and we've taken it all out and resprayed the arch with sprayed concrete and put it back in a more logical fashion. This is one of the blind shafts at Old Hill Tunnel near Birmingham, and at some time or other, that it had been left open as a ventilation shaft. You can see the ring of the brick eye there, and then they put a frame in there of some description we've got no records of, and they've filled it with concrete and abandoned the shaft. And another one of my favourite tunnels, one of the first I actually worked in, this is Conisborough Tunnel, and these are wrought iron plate girders built as a secondary lining. That's the original lining, original sidewalls, the buyouts I mentioned earlier for repairs, and this section of the tunnel, 24 feet there, was so badly distorted, they actually put these wrought iron frames in. This is a short repair section. It's only 4 frames. Behind you in the picture, further on, there's 27 of these frames. And they've basically put an extra lining inside there to stiffen the tunnel up. And of course that, as times has changes, causes a lot of problems with the size of vehicles going through there. We've had to take these out. Shackleton Tunnel was one of Brunel's 20-foot diameter shafts, very alternating 20 foot and 10 foot. And he had a problem with his heading down below, had to abandon it, raise the tunnel, and left the actual shafts going through. We had to support the rails over those. That's one of the rails that were put in at one time, beams to support it made out of bullhead rails. This is Peep Tunnel, again down in Hastings, through clay, which expanded and caused a lot of problems with the tunnel. So they built a concrete invert, and they used cast iron rings by Dorman Long. Almost finished. This is, I thought you'd be interested in this. Is well, I'll say Curran Tunnel, 1907. It's been built before then, and it was a brick tunnel, and it was very badly distorted. That's it now. Again, a photograph from Graham Bickerdike. And this is what happened in 1907. The tunnel was so badly distorted, they had to break it out and replace it. And it's a single track tunnel. They put this temporary shield in there, and then working from there, from platform and above, the men progressively broke out the brickwork and replaced it with these special cast iron rings. And the trains kept running while they were doing it. So that's, again, health and safety in 1907. Thank you very much. I hope you found that interesting. It's been a quick rush through. And Normally when I do this lecture, it takes about 2 hours. I've got a lot more slides than that, but I've had to cut it back quite drastically for today. So I'll hand back to Kate if there's any questions, and they'll fire them through to me.
So thank you very much, Peter. I think you will all agree with me that that really was a most informative and extremely comprehensive insight into how tunnels were built in the 19th century. And I can see that we do already have several questions. So I think just pop those up. So I think let's see if we can pick some that are ideal for answering. So where do we want to start, Peter? You did it helpfully, just highlighting some. So we start from the top. What have we got?
How would they fill the ground between the original ground and the tunnel lining? On the side walls, you're building them either vertical or substantially vertical. So you will probably have very little material to fill at the back of those. Your problem becomes as you start to build the arch up, if you've got overbreak. And very often you see on the drawings, it'll say any void is to be packed with mortar or material. This is the Victorian period. And although we admire the Victorians very much for the things they've left us behind, some amazing structures, tunnels is one where it's sometimes not so good. And very often they didn't fill the voids at the back, even when the drawings actually say they should. And we did have one situation at Standedge Tunnel where in breaking part of the tunnel lining out, and it specifically said on the drawings there that any voids to be filled with mortar and mortared rubble. It was all loose rubble, and we had a drop of a couple of hundredweight of a couple of cubic meters of loose material dropped out from the back. So very often they didn't fill them, even when they were supposed to. And as you saw from the pictures over the crown of the tunnel, they would simply just leave the voids up there if the ground was self-supporting. Next question I can see here from Naif Al-Hadid. How were ground movements controlled when tunneling in urban areas? Fundamentally, they weren't. They had no means of controlling ground movement. I did note that Hybel Road Tunnel in Macclesfield and the next one along Prestbury, they started in the town and went under fairly rural area, and they were in basically sand, and they were fairly shallow. I think the cover to Prestbury was only about 10 meters, and if you walk over the line of the tunnel over the farmland there, you can actually see a depression in the ground, and the ground dropped about 150 mil. I mean, it was sand, so it's it's susceptible to that, but they had no means of controlling it other than by timbering out the excavation. Can't see the next question is from Reg Smith. Is that Reg Smith who used to work for Donaldson Associates? Why would they build brick piers rather than backfill over the Overbreak? They would build the brick piers because they're simpler and easier to build, rather than that void above that tunnel was about 550, 600 mil. To get in there and backfill it with granular material would have been labour intensive, whereas just building those simple brick piers was considered sufficient at the time.
What have we got next? I can see there's a couple more.
Right.
We scroll down a little bit for Peter on the.
Okay, there's such a lot here. Right. Are Network Rail still running the tunnel management strategy project? That's from Chris Jack. Hi, Chris. No, the tunnel management strategy is in effect complete. We have done a few more tunnel management strategies, and we've updated a few over the years. But substantially, every tunnel has a tunnel management strategy. And also, where are they with the hidden shafts? We've spent quite a lot of time over the last few years working with AMCO and various other contractors to locate hidden shafts. A huge number have been located now, and we're moving into the next phase now of deciding what to do with the shafts. And some are being investigated and broken into, lasered and cameraed from the inside, or if they're filled, we need to find out whether they're filled or not. So that's an ongoing process. Crikey.
Certainly been a very active.
You mentioned
chat tonight.
Graham Hobbins. You mentioned the circular brick 6-foot drain being a feature of Southern Tunnels. Was there a particular reason for this? No, I think it's just something that the engineers who were designing one particular tunnel would come up with, because there were a lot more different railway companies in those days than we have now, and they were all individual private concerns. Sometimes it must be down to the individual engineers. I know that certainly in Stephenson's, he built the vertical sidewalls ones, really down to the engineer at the time. But those large circular ones, those large arch-shaped ones, are very much a Southern England feature. Would they have used lime mortar in the early years? Yes, right. Well, I deliberately shortened this talk, and I took out the slides talking about mortar. And yes, it would have almost certainly been lime mortar. And that lime mortar with a strength of what? Half a Newton, 1 Newton, 1.5 Newtons. Very, very low strength. Occasionally, on the drawings, you will see brickwork in cement. And by saying that, they are saying this is not a lime mortar, this is a cement mortar, rather than just lime and sand. That's uncommon. And a very, very strange one you'll see is Roman cement. Tunnels, brickwork in Roman cement. And that's not very common at all. Roman cement was used by Brunel on the Thames Tunnel. It's called Roman cement. It's nothing to do with the Romans at all. It's a reddy brown colour, like the terracotta colour that you get in some Roman features. So it has that name, but it wasn't actually invented by the Romans. And Roman cement is rapid hardening water. It'll go off like the clappers. It'll go off in the wet, and that's why Brunel used it on the Thames Tunnel. So if you ever see a drawing which says brickwork in Roman cement, you know that during construction they must have one hell of a water ingress to use a very expensive rapid hardening cement. How did they deal with groundwater when encountered during construction, hard rock and soft rock areas? If you're in a soft ground tunnel, what you will probably find is they will then start to classify the ground as being heavy ground, and the actual length of the advance would become much shorter, and they would use a lot more timber. By the English method, where we had the bottom heading, the heading itself would act as a drain, so you would be able to get the water away. But the whole story of sinking tunnels and pumping water, it's so common that they had sometimes to sink extra shafts to pump through, and that's the story of Kilsby Tunnel. The number of shafts they had there, the ones which were used as purely as pumping shafts. And then in rock tunnels, well, the Severn Tunnel itself, Walker's book, very good read. It's a nice book to read about how they actually dealt with the water that they had there. the problems they had when the tunnel flooded, when they went through the Great Spring, and how they actually built extra shafts and installed the enormous pumping engines to pump the water out. So it was a problem, and it was dealt with on an ad hoc basis.
I think there might be one bit further up that we missed from Claudio. Just how much maintenance?
Oh, right, yeah.
Yeah, I think we missed that one.
How much maintenance typically over 100-year-old tunnel required? It's very variable. Some tunnels are in extremely good condition. Network Rail have a fantastic regime for inspecting their tunnels, very, very logically arranged, very intensive annual inspections, and they maintain them on the basis of those inspection reports. Some tunnels are almost perfect after all these years. Some are in very poor condition. Some have been relined several times already, historically. One thing we do find is that low quality brickwork is a major problem. The bricks weren't as well fired as we fire bricks now. And we do find that some tunnels have been relined or extensively relined in the back end of the 19th century and the early 20th century. And then that continues. One thing that Network Rail are facing is that they have, because they have now such a very well organised inspection regime, they can actually detect that, yes, we have a trend that tunnels are needing more and more repair works. And at the same time, we're under pressure to put more trains through on the network. So the amount of time for maintenance is going down all the time. So it's not an easy question to answer how much time does a tunnel require, because they're all so very different. Some need very little, others are a continual worry. Indy. In tunneling, the surface settlement trough changes its original shape in the presence of surface structures, normally caused by rigidity. Sorry, I've lost that one. Or is there another reason? I'm not quite sure what you're getting at there, Indy. Certainly, there is far less control in the tunnels done in the Victorian period because of their timbering methods, and they weren't able to control excavation as we can do now. No, I'm not sure I can really answer that question. Tunnel shape. Yeah, tunnel shape. Southern England tends to be more clay. Yes, that's very true. A lot of the tunnels in Southern England will have that horseshoe profile, and a lot of them will have an invert. But further north you get better ground, you'll end up with vertical side walls and probably just a single circular arch roof. It all depends on the ground conditions and what they think they can get away with at the time. They wouldn't, build an invert if they could possibly manage without it. Got a message from Drew Howarth. Hi, Drew. Well, thanks for the talk. I can recall a time when I was small, but I can't read the rest of the message actually. Drew said he recalled his father had taken him to Standard and explained to me how the engineers had used the Canal Tunnel to construct the railway. Yes, you didn't believe him at the time. Well, they did. Yes. There's so many questions. I can't see them all, but will the presentation be made available? Do you have a recommended reference list? Well, the references I gave, Sims, practical tunneling, most of the illustrations came from there. Ripper is a smaller book, and again, wealth of information in there. And so Thomas Walker on the Severn Tunnel is an extremely good read. And Graham Bickerdike's website, Forgotten Relics, there's a massive amount of information on there on tunnel construction and the history of the tunnels and all the things that went wrong while they were being built. So will the presentation be made available? I assume that yeah, there's a recording being made of this, and that will be made available by the BTS later on. Is that correct?
Yeah, so this presentation will be available to view on our YouTube link for as long as this site is available. So yeah, if you follow this same link, you can watch this back at any time. I think I had one question for you. You mentioned you had a favourite tunnel.
Yeah.
And I just wanted to know why, because obviously you've mentioned so many.
Stand Edge, because it's formed out of the last 24 years. I've probably spent 2 or 3 years working on various problems with that, and I spent quite a lot of Saturday nights and Sunday mornings in the Stand Edge Tunnel, working night shifts, supervising drilling and cutting out the brickwork and spraying concrete. So yes, and then sleeping in the car park at Marston Station and waking up sometime in the morning wondering where the heck I was. Yeah. So yeah.
You got to properly explore it then.
Yes. There's one really nice feature about Stand Edge Tunnel. Between the North Tunnel and the Centre Tunnel, at one point, there's a chamber called the Cathedral with the most fantastic cast iron ribs supporting the brickwork, and it's really an amazing piece of structural engineering in the middle of the tunnel, and it has this nickname as the Cathedral. And Ian Wilson from Network Rail, you know, he says it's one of his favourites. It's his baby. Yeah, if I could have got in there, I would have liked to have been married in the Cathedral in between the tunnels at Stand Edge Tunnel. I think that would be quite an experience. Yeah. Anyway, yeah.
Maybe, yeah. Plan for hidden underground.
Yeah.
Okay, well, I think if there's any more questions that appear, I'm sure we'll make sure that they're passed on, that Peter gets to see them.
Yeah.
If you can answer any more. I'm sure also there's probably the potential that I'm sure the BTS June members might also be talking to you about whether there's potential for a part 2, as I think certainly a large amount of things you've covered tonight. Probably, like you say, even more that could be explored.
Yeah, I do the talk. I've done it a couple of times at Warwick University in a connection with their tunnelling course, which was partly set up by the BTS.
It is, yeah. Well, that's fantastic. I was going to definitely suggest that we extend this further. So thank you very much for your time to give that presentation tonight, and I've been pleased to see how many people we've had here on YouTube tonight.
Yeah.
Normally this would be the point where we gave you a round of applause and gave you our thanks in the best way, but for me, thank you very much for your time.
Thank you. I really enjoyed that. Thank you very much.
Okay, we've just got a couple of announcements tonight on behalf of BTS. We could just move to the next slide. So this is just a little bit of an update. We had our AGM last month, and we have since had to correct a slight constitutional procedural issue. I would like to announce that the 4 new members of the BTS committee for 2020 are Alistair Smith, Christophe Eberle, Jerome Berger, and Mehdi Hosseini. I'd also like to highlight just some of our upcoming events. BTS June members have actually got an event next Tuesday. It's a lunch and learn on how to design rubber products to make an immersed tunnel watertight. And if you come to this YouTube channel, you'll be able to join the event. We then have another joint event on the 16th of July with TAC Young Members Group. This is on time-dependent deformations of shafts and tunnels in the Greater Toronto area. Again, if you come to this YouTube channel, and hopefully we're going to, I think we've got another slide in a minute about how you subscribe, you'll be able to join this as well. Here we go. So yes, this is how, if you're interested in what you've heard tonight, and also in terms of looking at some of our other events that we've had in the past, please subscribe to our channel. It will highlight to you when our events are, and you'll never miss a lecture recording. In addition, we have also got a consultation out at the moment for the 4th edition specification for tunnelling, and we really welcome any comments. So please, if you could follow this link to our page and provide your comments, we are taking all of them into account so that we can update the BTS spec. And in terms of, rather than emailing, if you want, please email following the link provided. Also wanted to give you just a little bit of an update on our BTS at 50 book. Next year we celebrate our 50th anniversary, and we've been really encouraged by the amount of stories and contributions that we've had to the book so far. There's been a lot of activity dividing it into chapters, and there's a lot of work that has taken place so far. So these will all be available for you to look and digest. So this is what it's hopefully going to look like, with lots of stories. So these are some of the sample layouts. So our aim is by September to be largely complete. Really, we're being ready for printing by December, and we're hoping our publication will link to our 50th anniversary, which is in March next year. So lots of work to do, and hopefully shipping and everything won't let us down. So what we would really like is any volunteers. The editorial team would be really pleased to receive any help, particularly in terms of things like fact-checking, identifying people in photographs, helping to get us the book to be the most amazing quality that we can get, and also helping with seeking permission to print from copyright owners. So please contact Ken, Sarah and Anita with anything you have. So one other ask, as you can see, this is just an update on how we're getting on with sponsorship in terms of contributing to bringing down the price of this book for our members. And we'd also like to distribute some free copies to key organisations and educational activities. So far, as you can see, we're making good progress, but we do still have some opportunities for you to be able to get your logo on this book and to really cement your company with this as well. There are still a couple of places left, so please look into sponsoring us if you can. As we say, please help us out. We do still need volunteers and sponsorship to finish the job. I think that draws us to a close for this evening. So we look forward to welcoming you to our next BTS main event, which will be in September. And we'll be in touch shortly with what the title of that talk is. Thank you for your time this evening, and stay well.